About 3 billion years ago, a gigantic asteroid from deep space crashed into the Earth, irrevocably changing the history of the planet. This event not only brought destruction but also marked a fundamental turning point for the development of life. This meteorite, dubbed S2 by scientists, was a massive mass of rock 40 to 60 kilometers wide, and when it hit, it released tremendous energy that brought the oceans to boiling point and scorched the atmosphere. The biggest impact in history. S2 was 200 times larger than the famous asteroid that wiped out the dinosaurs, measuring about 10 kilometers across. This giant mass of rock created a crater in the Earth's surface about 500 kilometers wide. The impact was so great that a dense cloud of molten rock droplets formed in the atmosphere. Professor Nadja Draben of Harvard University describes it as like a storm of molten rock droplets falling from the sky. The heat released by the impact evaporated water hundreds of meters deep in the oceans and raised the temperature of the atmosphere by up to 100 degrees Celsius. But this was only the beginning. The collision created giant tsunamis and covered the land with huge clouds of dust. Sunlight could no longer reach the Earth, and simple photosynthetic life forms were completely wiped out in the process. Post-apocalyptic transformation. While the devastating effects of this catastrophic event may not be promising at first glance, scientists have discovered that this event opened new doors for the evolution of life. Research at the impact site known as the Barberton Greenstone Belt in South Africa found that the impact of S2 brought elements critical for life, such as phosphorus and iron, to the surface. These elements made it easier for the first microbes to access energy sources. Professor Draben explains the impact's effects on life as follows. When you brush your teeth in the morning, you kill most of the bacteria, but by the evening they're all back. That is, life has a resistance mechanism that cannot be destroyed, and thanks to this mechanism, life recovered surprisingly quickly after the impact and became more complex. The transforming surface of the planet. At that time, the Earth was not a planet covered with large continents as it is today. Most of the planet's surface was covered by oceans, with only a few small patches of land rising up in the middle of the seas. The collision of S2 created giant waves in this water world, upsetting the seabed. The iron-rich waters that rose to the surface from the depths provided vital nutrients for early microorganisms. The energy from the collision also reshaped the Earth's crust and dispersed elements across the planet. Critical substances for life, such as phosphorus, were mixed into the water by the impact, which led to faster evolution of organisms. This event demonstrated once again how powerful the adaptive capacity of life is. The chaos of space and the resilience of life. For the first 1.5 billion years of its formation, the Earth was constantly bombarded by giant debris from space. These collisions shaped the planet's surface and ignited the first sparks of life. The impact of S2 is considered one of the most dramatic examples of this destructive cycle. But the effects of this event were not limited to destruction. The new chemical conditions on Earth after the impact created a unique opportunity for the evolution of life. Immediately after the impact, the atmosphere was covered with dust and rock particles, cutting off sunlight and causing a severe cooling of the Earth's surface. However, the massive amount of vapor released into the atmosphere as water evaporated led to heavy precipitation on Earth after the impact. This rainfall washed minerals released from the rocks that hit the surface into the seas, radically altering the chemical balance in the oceans. This new balance led to the proliferation of substances such as phosphates and nitrates, which provide both energy and nutrients for microorganisms. Barberton Greenstone Belt, a time travel. The Barberton Greenstone Belt in South Africa is known as one of the sites where the S2 asteroid hit the Earth. Scientists focused on this region to study ancient rock fragments buried deep beneath the surface. These fragments had been altered by the intense pressure and heat of the impact. Hundreds of kilograms of rock samples were collected and analyzed in laboratories. These analyses provided valuable information to understand the effects of S2. It is clear that this impact marked not only destruction but also rebirth in Earth's geological history. Professor Draben expresses his fascination in exploring this region and discovering how the impact's enormous energy played both a destructive and constructive role. The rock layers in the Barberton Greenstone Belt may also contain the first traces of life. This makes it not only a collision site, but also an important area for understanding the origins of life. Post-collision oceans. The impact of S2 destroyed hundreds of kilometers of ocean floor, and massive tsunamis completely transformed coastlines. Although the coasts at that time were not home to an ecosystem in today's sense, a critical question was how the energy released by the impact affected ocean chemistry. The huge pressure waves created by the collision brought iron-rich water that had accumulated in the depths of the oceans to the surface. This iron provided energy for simple life forms and represented a new step in the evolution of life. After the collision, this iron and phosphorus spread across the surface, allowing simple single-celled organisms to multiply rapidly. These organisms were among the first species capable of photosynthesis, which led to the accumulation of oxygen in the atmosphere. This process paved the way for an important turning point in Earth's history, known as the Great Oxidation Event. Evidence of the power of life. Professor Draban's team has found plenty of evidence of how life returned after the S2 collision. This evidence shows that life was not only resilient, but also had the capacity to quickly seize opportunities. The chemical environment created by the collision functioned like a laboratory, providing the basic building blocks of life. After the collision, microorganisms multiplied and differentiated at an incredible rate, researchers say. The chemical reactions occurring on the ocean floor at the time not only supported existing life forms, but also increased the evolutionary potential of life. The role of phosphates and iron in this process is also important in modern biology. These elements are vital for fundamental processes such as DNA and energy production. Evrimsel miras SA2 çarpışmasının bıraktığı miras, yalnızca jeolojik katmanlarda değil, aynı zamanda biyolojik çeşitlilikte de görülüyor. Bugün bildiğimiz yaşam formları, bu tür devasa çarpışmaların ardından oluşan kimyasal ve fiziksel değişimlerin bir sonucudur. Çarpışmalar, yaşamın yalnızca yok oluşla değil, yeniden doğuşla da tanımlandığını bir kez daha gösteriyor. Profesör Drabo'nun belirttiği gibi, bu çarpmalar yaşamın gelişmesini sağlayan elverişli koşullar yarattı. 3 milyar yıl önce gerçekleşen bu felaket, bugün bildiğimiz yaşamın temel taşlarını oluşturan bir dizi olayı tetikledi. Belki de gezegenimizdeki çeşitliliği ve karmaşıklığı bu tür devasa çarpışmalara borçluyuz. Uzayın kaosu ve dünyanın direnci, yaşamın varoluş mücadelesindeki olağanüstü dengesini bir kez daha gözler önüne seriyor. Her felaketin ardından doğan yaşam, bize bu direnç ve adaptasyonun mucizelerini hatırlatıyor. Kim bilir, belki de bizler, 3 milyar yıl önceki bu dev çarpışmanın yankılarının birer kanıtıyız.